right, welcome everyone to our ASEG webinar series. My name is Kate Robertson. I'm the President-elect of the ASEG. Today we have a webinar by Dr. Mehdi Tork Qashqai, who will be talking about seismic imaging of the crust using Bayesian joint inversion of teleseismic P-wave coda autocorrelation waveforms. But I just have a few housekeeping slides to go through before we get started. I'd like to start by thanking our corporate and corporate plus members of the ASEG. So our corporate and corporate plus members make a financial contribution to the ASEG, where some of this funds go to the ASEG Research Foundation, which supports honours, masters and PhD students who are doing projects in geophysics. And the other funds go towards the ASEG to help support the running of the society. So a big thank you to our Corporate Plus members, High Size, Total Seismic and Bell Size. And thank you to our corporate members, Southern Geoscience Consultants, Transparent Earth Geophysics, Santos and Down Under Geophysics. And we also have one new corporate sponsor. So welcome to them who've just come on board. Australian Geophysical Services. Based in Queensland, Australian Geophysical Services provides surveying services across mineral exploration, geotechnical and energy domains. So thank you and welcome to them. I'd also like to thank our branch sponsors who help our branches to give benefits to the members in their region. So in South Australian, Northern Territory, New South Wales and WA, thank you to all of these sponsors mentioned here. And if you'd like to get on board becoming a branch sponsor or a corporate plus member, then just let us know, reach out to us through the ASEG website or through email. So for the running of the webinar today, we will be asking allowing an opportunity for questions at the end. You can type your questions throughout the talk using the Q&A feature. So this is usually found on the panel on the bottom, but it could be somewhere else depending on the version. Or if the Q&A function is missing, which is what happened to me last week, but is there this week, you can type it in the chat box. So it can be a bit fiddly, so chat's always an option if you can't find that. And at the end, when we get to the questions, if you'd rather ask it verbally, just use the raise hand function and we'll get to you when we can. We've got another webinar coming up on Tuesday, 16th of February with Dr. Kate Selway, who'll be talking about exploring for minerals, not anomalies, and developing quantitative interpretations of MT models. So you can register for that now through the ASEG website in the events section. And I'd like to remind you of the benefits of being an ASEG member if you aren't already. One of the biggest benefits is the highly reduced admission to the AEGC conference. So that's in Brisbane in September this year. So that alone outweighs the cost of your membership. So if you've thought about being a member, now's a great time to join. You get free access to our technical journal, Exploration Geophysics, free copies of preview posted to you every couple of months, along with a range of other benefits, including our annual wine offer. Again, financially can outweigh the cost of your membership and it's a great perk. And we've got lots of social and networking events, but also technical events held usually around monthly in each state. And if you want to know more about the Society or geophysics news in general, latest events, follow us on social media. We're on Facebook, Twitter, LinkedIn. And the video for this talk and all of our other talks are found on our YouTube channel, ASEG Videos. And so moving on to the webinar now, we have Dr. Mehdi Tork Qashqai presenting today. So in November 2012, Mehdi joined the PhD program at Geodynamic and Geophysics Group at Macquarie University in Sydney, Australia. His research focused on the development and implementation of a multi-parameter geophysical inverse modelling tool known as LitMod. In August 2016, Mehdi completed his PhD entitled Multi-Observable Probabilistic Inversion for the Thermochemical Structure of the Lithosphere. Prior to his doctoral study, he was working in the oil and gas exploration industry for 6 years as a seismic processing and team leader geophysicist, delivering processing, imaging and quantitative interpretation of seismic data. He joined the CSIRO Deep Earth Imaging Future Science platform in July 2017 as a postdoctoral fellow. He is currently a research scientist at CSIRO DEI FSP, and his main research in the geoscience imaging pillar of the DEI research is focused on the developing and application of new passive seismic imaging approaches to obtain better tomographical models of subsurface structure across multiple scales, from the exploration scale to lithospheric scale. I'd like to introduce and welcome Dr. Mehdi Qashqai, and I will turn off my screen sharing and invite Mehdi to share his screen and to start off his talk. So thank you very much, Mehdi.
No worries. All right. Let me share my screen now. Thank you, Kate, for introduction. Let me just share that. And yeah, thanks for the introduction, and thank you for giving me the opportunity to present my research. So I hope that everybody see my screen now. Can you see that? Okay.
Yes, we can
All
see
right.
that.
All right. Hello, everyone. Thanks for attending to this webinar. And in this webinar, I'd like to show how we can image the subsurface structure below a receiver, a seismic receiver, using joint inversion of teleseismic P-wave coda autocorrelation waveforms. I should acknowledge my colleague Edin Sagin, who helped me in this development of this new approach. Thanks to him, and thanks to CSIRO for its support, CSIRO Research Office, and also the management team. At the beginning, I need to give you some introduction, a background about the teleseismic waves that we use, because we're trying to invert and basically some delay time and amplitudes of some specific phases. So I need to give you a little bit of introduction. Sorry for those people who are expert in this domain, and I need to do a bit introduction about this. Sorry for that. And how we can explain how we can construct the responses of the subsurface structure to an incoming teleseismic P waves in the forms of receiver function and also autocorrelation waveforms. And why we do the autocorrelation or why we do the joint inversion of the autocorrelation of radial and vertical component. And I give you the reason for motivation of this study, and also I show you the feasibility of the approach using some synthetic and real data tests. So now we all know that if we have a distant earthquake happens somewhere around the world, we can record it seismic waves on the surface of this Earth and many kilometers away, many thousand kilometers away from the epicenter of the earthquake. So the first wave obviously is P wave that will arrive and we can record it. And then we have S, and then we have surface waves. This talk is concentrated on the P waves and its coda parts. So we focus on the reverberation after the onset of the P wave. And there are some assumptions, plane wave approximation. So which is a valid assumption at epicentral distances between 30 and 90 degrees because of a large curvature of the wavefront at these distances. And also we assume that P wave arrivals are larger on vertical or S waves are larger on radial component. Now, obviously the first wave that will arrive P wave. So we zoom out on the target area here. The first wave is P wave, and then after that we have P-to-S conversion from below receiver. So in this example, we assume we have one layer of crust over a half space, which is upper mantle. And another phase is basically a reverberation of the P wave within the crust, within the layer. It's PP phase. And then another one is a mode conversion phase, P-to-S. We have P, and S phase. So it has two legs of P and one leg of S. And this arrives with this wave, which has two legs of P in common with the previous one and one leg of S. And then we have P-P-S-S. So we have two conversions, one from the surface and another one from the bottom of our model, and then reflect back to the seismic receiver. And this arrive at the same time of this reverberation, which has two legs of S and one leg of P in common with the previous one. Obviously, this is a very simplistic view, and real structure below the seismic receiver might be more complex. You might have some multiple layers, like 2, 3, 4, 5 layers below a seismic receiver, and that's why we're trying to invert these amplitudes and travel time, these seismic waves. So the first Earth response that I'd like to briefly introduce is receiver function. Receiver function, which I show you for one layer crust over a half space with this properties like thickness of 35 kilometers, VP of 6.65 and VS of 3.69. I tried to calculate the receiver function for such an Earth model. The receiver function, most of you know that, is just the convolution of the vertical from horizontal or radial component. And we're trying to basically isolate P-to-S phases from the P waves. And by the convolution, we're trying to calculate the delay times of each of these phases that I show here. And also they are the same as the previous phases that you saw in the last slide. So by the convolution, we're trying to calculate the delay times between P to S, for example, and the direct P waves, which arrive at the zero lag time. And we can calculate the travel time of each of these phases with respect to the direct P wave. So, and if anyone can actually calculate these equations, and we can find thickness of the crust and also the VS or VP of the crust by using these equations. Another one is autocorrelation of the vertical or radial components, which is basically reflection response below a seismic receiver. And I'll let you know in the next slide that why it is a reflection response below a seismic station. But if you look at carefully in these three types of signals, on vertical autocorrelation, which is shown by red, and radial autocorrelation, which is shown by blue, we have pretty much same phases as we can see in receiver functions. But as you know, receiver functions, because we used the convolution, we have very weak or no sensitivity to P. However, we have additional information on radial and vertical autocorrelations. In 1968, Clebot showed that the transmission response can be converted to the reflection response, and show you why this is the case in this slide. As I said, by autocorrelation or deconvolution, we're trying to isolate phases with respect to the direct P waves. So if I calculate the travel time difference between the direct P and this reverberations, PPP phase, this time difference would be equivalent to seismic waves that travel from surface reflected back from the bottom of the model and reach to the receiver. So it's like you can interpret that as a reflection response below seismic, as if there was a virtual source here. And then similarly for this is for only P, this phase, P and P phase. And the same principle valid for this phase, which is P, P, S, S. And if I calculate the travel time difference between this P, which is shown by blue, direct P waves, and also this yellow one, this delay time is equivalent to delay time of the, as if there was a virtual source here. So that's why we call it a reflection response below a seismic station, as if there was a virtual source there. So the idea here in this presentation is to generally invert autocorrelation of the vertical and radial components, because we have both sensitivity to VP and VS, and we can better constrain the VP-VS ratio. I will show you in the next couple of slides the feasibility of that with synthetic test, and Before that, you might ask why, what is inversion? And so I repeated several times during the previous slides that inversion is basically a process that we're trying to model the subsurface of our system using data that we measure on the surface or any parts of any depth of the subsurface. So the first thing is we prepare the data properly, and then we try to parameterize our system. For example, the 1D Earth below seismic station, we parameterized with a few layers. We assigned VPVS density and thickness for each layer. Then we try to calculate the synthetic seismogram and compare it with the data, with observed data. And then if the difference is very small or small enough, if we are happy, then we can accept the model parameters. Otherwise, we try in another model. And then we repeat it many times in order to find a reliable solution for our problem. And why large scale lithospheric structures are really important for exploration geophysicists. This might not be really clear, but the studies show that the deep crustal structures are really critical for controlling and developing the mineralization. And previous studies show that the world-class giant deposits share a common lithospheric settings. For example, the craton margins play an important role on the location of the iron oxide copper gold deposits at global scale. One example is Olympic Dam, which is in South Australia and situated close to the margin of the South Australian craton. There is a big Moho offset there, so we have a transition from the crust to upper mantle, and this transition is very rapid. So obviously, understanding better the subsurface structures below these giant deposits can help us to figure out and find maybe the other giant deposits around the world, or including in Australia. Also, we all know that the elevated crustal temperatures can be linked to basically hot materials in the crust, and also VPVS ratio is really, really sensitive to changes in temperatures or presence of the melts or presence of the fluids, and also is a good indication of the composition of the crust, like felsic or mafic materials in the crust. So I hope that by presenting this research, I have a very small contribution in better constraining the VPVS ratio, and as a consequence of that, bring additional information to our understanding about the subsurface and tectonic setting of our continent. Now I move to synthetic inversion tests. So I'm trying to test the feasibility of the joint inversion to see whether we can better constrain the compared to the inversion of either a receiver function or the inversion of the vertical autocorrelation, which I did in 2019. And for that reason, I created some synthetic data, synthetic receiver functions, synthetic autocorrelations of the vertical and radial component using a 4-layer Earth model. And in this slide, I only show you the results of the inversion for VPVS ratio only, because that's an important parameters. If we can constrain it really well, then we have a good estimate of VP or VS as well. So I did 3 inversion tests: inversion of receiver functions, inversion of the vertical autocorrelations, and joint inversion of the vertical and radial autocorrelations. I need to mention that I applied bandpass filter before and after autocorrelation of the synthetic seismograms in the frequency range of 1 and 2 Hertz. So as you can see here, the magenta color is the true VPVS, and the blue is the mean of the posterior distribution. So you can see an inversion of receiver function or inversion of the vertical autocorrelations, because we do not have enough sensitivity to either VS or VP, and the VPVS is not very well constrained. On the other hand, because we have good sensitivity to both VP and VS in autocorrelations, then the joint inversion of the vertical and radial autocorrelations can give a better estimation of the crustal properties. So you know that you see that here, the high probability area basically contains the true model. And this is the feed to the data, receiver functions on the left, top right is the feed to the inversion of vertical component autocorrelation. And the bottom line is showing the feed to the autocorrelation of the vertical and radial. And as you can see, in the inversion of the only vertical component autocorrelation, we have some problems in fitting these two phases. However, in the joint inversion, with the same parameters, with the same inversion, we can fit it much better than single inversion. And the blue is the mean of all accepted models, which are shown by gray colors, and magenta color is the observed data or synthetic data. We applied the joint inversion on real data recorded on the Bilby passive seismic line in Central Australia. And as you know, it's crossing, it's very long passive seismic line. It's crossing several geological blocks across Central Australia. It's extend from Gawler Crater in the south to the basically north to the Georgian Basin, Northern Territory in Australia. And we have some active seismic line along this passive seismic line. One is Goma line, another one 9GA, which were operated by the GA. And at the end of this presentation, I'm trying to compare the MOHO estimates from the joint inversion with the Goma active, the interpretation from the Goma active seismic line, and also with the other MOHO estimates from the other studies, including those MOHO and our study in 2019, and also with the receiver functions. I provide you two examples. First example is one of the examples associated with the station BL22. I show on the top left figure the feed to autocorrelation of the vertical and radial components. Similar to synthetic tests, the magenta color is observed data, and the blue is the mean of the best accepted models. And in below panel, we see the posterior distribution of the VP-VS and also the VP-VS ratio. This station is situated on a sedimentary basin, an officer basin, and basically here, we found a low VP and low VS in the top 5 kilometers, which represents location sedimentary basin, officer basin. So, and then on the right-hand side, you see the example number 2 for station BL05, situated in the north of the passive seismic line, and then feed to the data is relatively well. And the bottom line is the VP-VS and VP-VS rate. And the shallowest mode found here in session BL05, I think it was 43 kilometers. And then if I joined 1D profile for 1D profile of VP-VS and VP-VS ratio for each of these stations along this red dashed line, I can provide a pseudo 2D profile along the passive seismic line. And the top is VP and the middle is VS, and the bottom line is VP-VS ratio. And then I presented the MOHO estimates from this study by black line, a solid line, and also MOHO estimates from receiver function by red, and MOHO estimates from our previous study, which was the inversion of only vertical component correlations in yellow or dark yellow color. As you can see, the receiver function and vertical correlation inversion give pretty much similar results, although we have some differences at some parts, but they are more or less consistent together. However, the joint inversion gives something very different. And I'm not saying that this is correct and this is right and the others are wrong, but it's good to compare it with the other methods like seismic reflection, which I did it in this slide. So this is Goma seismic line, Goma migrated seismic line, taken from the GA website, and I basically determined the tectonic blocks on the top of this seismic line, and then the stations with the red color here, and the north is this way, and then south is left hand side, and the interpretation from the seismic reflection are shown by green color, and larger scale structure are shown by brown here. Thanks to Michael DeBlayer and Nico Markham from GA who provided this interpretation with us. They share it with us. Thank you very much for that. And the receiver functions, Moho estimates from receiver functions shown by red. Moho estimates from inversion of the correlation of the vertical component shown by yellow, and Osmoho by blue. And this is study basically Moho estimates from our study from joint inversion shown by black. Obviously, this is two-way travel time, and the y-axis is two-way travel time, but Moho depth is in depth domain. So I used for converting the Moho depth obtained from this study to time domain, two-way travel time domain, I used our VP velocity models here to convert it to time domain. And for the other Moho estimates from the previous studies, I used a constant velocity of 6 kilometers per second to convert from depth domain to time domain. As you can see, results from this study are more or less compatible. The general trend of that is more or less compatible with the interpretation from the seismic reflection. And also you can see the fade of reflectivity at the base of the crust in the seismic image basically corresponds to the Moho depths that we estimated from the joint inversion. And we got the uplift of the muscular province here as well. You can see the Moho estimates from the other studies are more or less compatible to each other. And the Moho basically decreases after the mass graves towards the south, and then again increases to the Galler Kraken to a depth of around 50 kilometers or more than 50 kilometers. This is the last slide. I'd like to conclude that we can take into account the variability of both VP and VS, and consequently the VP-VS ratio by joint inversion of the vertical and radial autocorrelation, because they are very sensitive to both VP and VS. And we know that the crustal VP-VS is a good indication of the crustal composition, and constraining this specific parameters, VP-VS ratio is identifying changes in compositions in the crust, and might help bring additional information. So we showed that this approach can give better estimates of the crustal properties, especially the VP-VS ratio compared to the inversion of either inversion of the autocorrelation of the vertical component or receiver function. And one advantage of this method is if you cannot find receiver function, high quality receiver functions around the world, I think autocorrelations are an alternative approach. So we can use autocorrelation instead of receiver functions because they are less noisier than receiver functions. And the joint inversion can be used in conjunction with the inversion of receiver functions to provide complementary information. Also can be used in conjunction with the reflection profiling to provide complementary information, especially at depths that we have penetration problems in seismic reflection. So, for example, mid-lithospheric discontinuities, mid to lower crustal depths, and also the base of the crust, which we have a transition from crust to upper mat. And I'd like to thank once again from Michael W. and Malcolm Nichol from GA for sharing their interpretation with us. And I'm happy to answer any questions if you have. Thank you.
Great, thank you very much. It was a really good talk. I do have a question that's come through. So if anyone has questions, put them in the Q&A box or in the chat. Or if you raise your hand, I'll try and keep an eye out for that as well. So we've got a question from David Annette. Great talk. I don't recall you mentioning noise. What noise levels did you use for your synthetic tests? Were these the same for VP and VS, and are these realistic?
So can I see the?
You should be able to see it in the Q&A.
Q&A, okay.
I can read it again if you like.
Yeah. For synthetic tests, I contaminated them by Gaussian noise. It's with a certain standard deviation. I think it was 0.05 or something like that. Yeah, it was a Gaussian noise basically. And the second question was.
Were these the same for VP and VS, and are these realistic?
Well, the noise is the same. Noise is the same for both autocorrelation of vertical and autocorrelation of radial components. So I basically contaminated the waveforms with noise and then trying to invert it.
Cool. Another question's come through from Son Pham. How do you take into account the oblique incidence from teleseismic P-wave arrivals in the synthetic experiments? Or do you only predict autocorrelation for perfectly vertical arrivals?
For this test, I basically use a constant slowness. I created the synthetic data with constant slowness, like I think it was 0.06 seconds per kilometers. Obviously, it's not vertical, but I tried to make the slowness parameters variable during the inversion, and I keep it basically in a narrow range around 0.06 second per kilometers. Yeah. And question was?
Got one in the chat from Anand Ray. Good stuff. How does this method compare to direct seismogram inversion by Jan Detmer et al. When he's posted a link in there? They do not require RFs and also invert for the noise.
Yeah, I've actually read that paper. I don't know. I haven't tried that to see what's the difference. Yeah, that's a full basically waveform inversion, obviously, I think, and they don't autocorrelate, or they don't use the I think a full waveform. But I haven't done that. I don't know what would be the difference compared to that. Yeah. Thanks for mentioning that.
And David has another question. Have you considered comparing your results with interpretations of MT data?
I didn't do that, but I think there are a few MT studies in the area around the southern part of the passive seismic line, and also in along with the 9GA seismic line. I saw some consistency with the VPVS values, like high and low VPVS, but I'm not really sure how we can interpret these things. So I didn't dive into that. So yeah.
Malcolm Sambridge, nice talk. How many MC-MC chains do you use, and how many forward models?
I use honestly, I use one chain, but it's Metropolis hasting algorithm, and I actually use, I think 300,000 samples for the forward model. So I use a total number of 300,000 model.
Cool. I can't see any more questions yet. think you may have answered them all. Nothing else coming through. Yeah, well, I think you've covered everything. So thank you very much for giving your talk today, and we'll make this available on YouTube over the next sort of coming days or next week. And you can check out other talks as well on the YouTube channel. So thank you very much everyone for tuning in, and big thank you to Mehdi for giving us this talk and sharing his work with us. So thanks.
Thank you very much, Kate, and thanks for attending. Thank you.
All right, thanks. Bye.